And you will say, what does that even mean? Well, again, suppose you have some data. So there, now we have a lot of data points. The first principal component about this data, about the centroid of this data is, we'll say that. That's approximately correct, don't you agree? What's the second principal component? It's going to be something orthogonal to that one, right? Now, if this were a multi-dimensional Gaussian point cloud, there would be that same number of dimensions of principal components that make it up. And if you were to compute all of them, you could exactly represent all of these data points in its principal components, right? Okay, well, let us suppose that you want the second principal component. How are we going to do it? And for this example, pretend this is a multi-dimensional cloud, not just a two-dimensional cloud as I have drawn here. So it's coming out of the board here, and there's plenty of other dimensions. I've already computed the first principal component. How am I going to get the rest? Yeah, so I'm going to use the Gram-Schmidt process to remove this component from the data. And by removing this component, I will be left with, and the only thing I can draw here is a, by the way, this x right here is the same as that x right here. I've shifted over here, but it's really going to be right there. Okay, I just shifted over here because I needed more space. Now, you see how when I remove that component, they've all been flattened to this line, but in hyperdimensional space, that's really a disk, right? Or actually, it's a k-dimensional who knows what thing. But there is no variance in the direction of that principal component. Why? Because I subtracted out all variance in that component direction using the Gram-Schmidt process. Now, if I have done that, is there still any variance here? Mm-hmm. Sure there is. There's obviously some in that one other direction, but if it were a disk there could be variance in two directions. And if it were a hyperdisk, I don't even know what that means, there's variance in the remaining directions I can't even point. Well, we can now find the first principal component of this data, right? And the result will be the second principal component of the original data. And it will guarantee to be orthogonal to the original first principal component. You can see that, right? Because everything's orthogonal in that space. And so the result will be that when you compute the first principal component of that, you get that one. And then we subtract out that, and that collapses it on that component as well. And whatever remains, we can continue repeating this process till we've got all of the principal components. What happens if we run out of principal components before the data runs out of dimensions? Meaning, suppose it's 10-dimensional data, and after we've computed only 5 principal components, then we're left with a whole bunch of points that are the same point. What does that tell you?
You've got unnecessary dimensionality.
Yeah, that means some of the attributes in your data were perfectly correlated. And if they were perfectly linearly correlated, then why do you have them? You're measuring the same thing multiple different ways. Even though they're different numbers, it may be very non-intuitive. You might look at your data and say, hey, look, it's a whole bunch of numbers, but really 2 of those values were saying exactly the same thing, just with different scales or different shifts or something like that. Okay, well, now we know how to compute principal components. Let us answer the more important and difficult question: why did we compute principal components in the first place? We went to all this effort to learn how to do it, but what the heck good is a principal component? Yeah, so it actually happens very often that you will, after computing a few principal components, there's just not much variance left. It doesn't always go straight to 0, but it usually goes to pretty darn small. And so we usually can say, hey, what if we just use the first 2 or 3 or 4 principal components, and it'll still capture 98% of the information in that data, and we've taken data that could have been 1,000 dimensions and reduced it to 2 or 3 dimensions, and it's just as good. Well, that's going to make our algorithms more efficient. It's going to do lots of good stuff, right? How do we do that specifically? Well, remember how we project by dot producting with a unit vector? Presumably these are unit vectors, and one of the reasons we know they are is right here. P is equal to t divided by d, where d is the magnitude of t. You see how this is normalized the vector step, and then we return p? In other words, this algorithm returns a normalized principal component. Some people like to scale the principal component vector by its eigenvalue, which is a measure of how much variance there is in that dimension. So in this picture, that would be something like this will be a really big principal component, and then this one will be a really stubby principal component. And graphically speaking, that kind of makes sense, right? Kind of fits with the data. Other people like to normalize all of their principal components to have a magnitude of 1 and separate the eigenvalues as a separate concept. And who's correct? Well, again, these are tools. There's not a correct thing to do. It's just you should be aware that this is something going on and you should know what it means. Therefore, you can use it to whatever way works for you. By the way, eigenvalues are actually squared, so they're not going to look like this. I kind of scaled them by the square root of their eigenvalues, and that looks nice. If you scaled them by the eigenvalues, then you end up with some non-intuitive scaling that's hard to reason about for me. Blah. Okay, so suppose I have this data, and I project every single point onto the first principal component, and the second principal component. What does that do? Yeah. Well,
then you know how much of the point is in those directions.
Yeah, I'm going to say how much of the point is in this direction and how much of the point is in that direction. Do you see that that's the same thing as the values in a point? That didn't come out very well. For example, we represent a point like this. Parenthesis, x, comma, y, close parenthesis, right? What does x mean? Well, x is how far you are in the 1, 0 vector direction. And y is how far you are in the 0, 1 vector direction. And these are the two vectors we're used to working with. But we could very well treat these principal components as their own sets of vectors, right? It's really just a case of take your head and come over into the space and go, right? And now you're looking at the graph kind of sideways. And you could project the points onto this diagonal graph paper and see where they are in this coordinate system. Another way to, if you want to see graph paper, because that helps you feel like you are in some space you understand, right? If I'm at 3, 2, I'll go 1, 2, 3, 1, 2, and then I'll plot the point right there, right? Well, you can project your points into the orthonormal dimensions, and that effectively has the effect, that's a great way of putting it, of rotating it, what's that, about 45? Nope, a little more. Rotate. Bear with me, I know you don't need the graphical demonstration, but it makes me feel better. It's as if we took our data and rotated the axes such that most of the variance is in the 1, 0 direction, and the second most variance is in the 0, 1 direction, and so on and so forth. And remember last time's lecture we were talking about how this is used in the domain of psychometrics, where they took the two principal component axes and then they colored them and called them red and blue and green and no, there's no green. Red and blue and white and yellow, right? Okay. Well, that's kind of what we're doing here too, is we're giving a very small, meaningful, hopefully meaningful, intrinsic representation of the high dimensional vector that you've done there. And that's called principal component analysis. Far more important than knowing what it's called or even knowing how to do it, because you can look those things up, is knowing why we do it and how it's useful and what it's accomplishing. And what it's really accomplishing here is we're reducing the dimensionality of data. We're finding what variance really occurs in the data, and we're using that variance as a basis for extracting the axes that we think are meaningful. And that is a surprisingly powerful tool for taking complex data that humans can't wrap their heads around and figuring out what important meaning is in the data. And that's kind of what they're doing here, and that's useful for all kinds of... Do you see that ultimately what we're doing here is we're solving the problem of perception? And by solving, I mean, we're starting to solve the problem of perception. Because we're taking, so your eyes, for example, have a retina, and the retina has a whole bunch of photosensitive kind of neuron-like cells. They're more, they call them rods and cones, but they respond to light, and depending on how much light shines on them, they fire at different rates and tell your neurons in your brain what's going on. Well, that information is actually upside down because it goes through a lens in your cornea, it turns it upside down, your brain sorts it all out, we all know that. But the point is, there's a lot of information coming into your head. Billions and billions of data points coming from all of the retinal cells, and somehow your brain takes all that information, processes it for a while, and what comes out are a few meaningful concepts that are extracted from what's encoded in that data. I see billions of points of light, and yet I know student, 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 not a student, that's a chair, that's a bottle, that's a computer, and that's part of me. And that doesn't seem that impressive, but try to make a robot do that. It actually is kind of impressive, and here's a start towards techniques for perceiving meaningful values in high-dimensional data. And so I've managed to talk you through steps 1, 2, and 3. By the way, this is the algorithm for computing principal component analysis. The word analysis is kind of vague and overused. It could mean anything. In this case, it means, hey, let's compute a whole bunch of principal components and project our data onto those several principal components. We'll call that principal component analysis because that's a great way to analyze hyperdimensional data. What is principal component analysis? Is it computing the principal components? Is it projecting onto them? Is it using those principal components for various purposes? I don't know. I don't care. Here's an algorithm that does it. I decided to divide these into training phase and reducing phase. I think that's an intuitive way to break this down. If you look up other principal component analysis algorithms out there, they might not break them up into these two phases. That's my own contribution here. But it makes sense to me. This training phase is where we're computing the principal components. We're saying these are the important parts of the data. The reducing phase is where you actually rotate the data onto those axes or do the projection. Sometimes all you want is the training phase. For example, sometimes what you really wanted are the principal components, and then you're going to throw out your data because you can go use those principal components for other purposes. So I like to separate this algorithm into two parts for that reason. Let's look at it really quickly. Let C be the centroid of X. As you know, it doesn't have to be the centroid. That's just a convention, but it wouldn't be called principal component analysis if you didn't do the centroid. You'd have to call it your own thing if you used the medoid. But it might be better. There are good reasons why the medoid component analysis, that wouldn't be right. Principal component about the medoid analysis might be more useful. Okay. Subtract the centroid from each point in X so that now we can use that algorithm up there to compute the first principal component about the origin. Then we're going to use the Gram-Schmidt process to remove that component from the data. And then P becomes a new row in M, where M is going to be the list of all your principal components. To reduce it, we just project onto M. Okay, I think you get it. Out of time. Thanks for coming.